Welcome to my online course in linear algebra. Today we will discuss linear combination if V1, V2 up to Vn are elements of a subset S of a vector space V over the field F, then the linear combination is given as alpha 1 V1 plus alpha 2 V2 plus up to alpha and Vn. This alpha i's belongs to the field F. The set of all linear combinations of the element of the subset S of P is called linear span of S. It is denoted by L of S. Next is theorem on linear span. First theorem is that linear span of a non-empty subset S of a vector space V is a subspace of P over the field F. Also, it is the smallest subspace of the vector space Pf containing S. Here, we have given a non-empty set S. We have to show that linear span of this set S is a subspace of the vector space P. And further, it is the smallest subspace of that vector space. That is, given any subspace W containing the set S, linear span will contain in that subspace W. Proof. Let S be a non-empty subset of a vector space Pf, then a linear span is given by the collection summation alpha I Pi. Alpha I belongs to S, alpha I belongs to F. Since S is given to be non-empty, so linear span is non-empty because linear span will be the collection of the element of the vector elements of S. Next, we consider two element X. Any element in the linear span is of the form summation alpha I Pi, and Y is of the form summation beta I Pi, where Pi comes from S and alpha I beta I comes from F. Next, we consider n b to be an element of field, then we check out what is ax plus by. Our ax plus by will be a into x, that is summation alpha I bi plus b summation beta I pi, which is equal to summation a alpha I pi plus summation b beta I pi, which is equal to this one. That is, we are taking summation common, then writing the element. Here pi is common, so I'm writing remaining element within the bracket. That is a alpha I plus b beta I, then pi multiplied with pi. Since AB belongs to F, alpha I beta I belongs to F, so F is a field, so A alpha I plus B beta I belongs to F. Also, Bi belongs to S. Therefore, Ax plus By is a linear combination of element of S. That is, we consider xy to be any element in the linear span, and AB belongs to F. Then we check out whether Ax plus By belongs to linear span or not. Now, here, by calculation, we have found that linear combination of Ax plus By belongs to linear span. Therefore, it satisfies a non-empty subset S of P to be a subspace. That is, xy belongs to P, AB belongs to F, Ax plus By belongs to the P belong to S, then S is a subspace. So Ax plus By here belongs to belongs to L of S. Therefore, L of S is a subspace. Next, we have seen if P belongs to S, then P can be written as 1P belongs to L of S. Therefore, S is a subset of L of S. Next, let W be another subspace of P containing S. We have to show that L of S is contained in W. For that, we will consider element summation alpha I pi belongs to linear span where alpha I belongs to pi belongs to S. Since S is a subset of W, pi belongs to W. Ultimately, this pi belongs to this W. Since W is a subspace of P, so W is closed under vector addition. So alpha I pi belongs to W as W is a subspace here. W is a subspace. W is closed under external multiplication. That means if I take an element from the field and element from the subspace, then their scalar multiplication belongs to the W. So alpha I pi belongs to W. Their sum belongs to W as W is a subspace. Therefore, linear span, this any element in linear span contained in W, that means linear span is a subset of W. So linear span is the smallest subspace containing S. Next is properties of linear span. If S1 and S2 are two subsets of a vector space S1 containing S2, then linear span of S1 containing linear span of S2. Take S1 containing S2, we consider any element in the linear span, that is summation alpha I vi belongs to linear span of the first set, then alpha I comes from the field and vi comes from the set. As S1 is contained in S2, that P1 that belongs to S1 automatically belongs to the S2 as S1 is a subset of S2. So P1 ultimately belongs to the S2. So alpha I vi belongs to S2 due to as S2 is a subset of P. So every element of S2 belongs to P. So F P is a vector space. So multiplication of scalar and the element of vector that belongs to S2. Again, summation linear combination alpha I vi belongs to linear span S2. Therefore, any element in the linear span S1 belongs to linear span S2. So we get the first property. Next, linear span of S1 union linear span of S2 is equal to linear span of the union of two sets. Since S1 is contained in union of S1, S2 and S2 is contained in union of S1 and S2, so linear span of S1 is contained in linear span of union of the two set S1 and S2. Similarly, linear span of S2 is contained in linear span of the two set S1 and S2. Therefore, if I take their union of this and with this, I will get linear span of S1 union linear span of S2 containing linear span of S1 union S2. So I will get the second result. Next, I'm going to prove the third property. That is linear span of S1 intersection S2 is equal to linear span of S1 intersection linear span of S2. S1 intersection of two set S1 and S2 always contain in the individual set, that is S1 and S2. Take the linear span, then linear span of S1 intersection S2 is contained in linear span of S1 and linear span of S1 intersection S2 is contained in linear span of S2. This come from the property number 1. So I'm getting here linear span of S1 intersection S2 is contained in linear span of S1 comma linear span of S2. Therefore, I am taking the intersection. This in the left hand side, it will be linear span of S1 intersection S2. In the right hand side, it is contained in the linear span of S1 intersection linear span of S2. That is, I am getting one part. Linear span of S1 intersection S2 is contained in the intersection of their individual linear span. Again, S1 is contained in linear span of S1. That is from the theorem. Linear span is the smallest subspace containing the set itself. So S1 is contained in L of S1. Similarly, linear S is contained in linear span of S2. I'm taking the intersection of this S1 containing LS1 with S2 containing LS2. I'm getting S1 intersection S2 is containing, it is a equal subset and equal LS1 intersection LS2. Since LS1 and LS2 are subspace, their intersection is also subspace containing S1 and S2. Okay, so here I am considering any element in the linear combination of their intersection, that is summation A1 B1 belongs to linear span of S1 intersection linear span of S2, then they belongs to their individual linear span, that is summation AI Bi belongs to linear span of S1 and summation AI Bi belongs to linear span of this is S2. Kindly correct this one. This is S2. Where Bi belongs to S1, S2 and for all I ranges from 1 to n, and Ai belongs to the field F. Since Bi belongs to S1 and S2, so Bi belongs to S1 intersection S2, and their linear combination summation Ai Bi, which is equal to A1 B1 plus A2 B2 plus dot 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 up to An Bn belongs to linear combination of S1 intersection Sn. That means I am considering any element in the linear span of their intersection of their individual linear span. I am getting that element in the linear span of their intersection. So this is subset of this set. That is L of S1 intersection L of S2 is contained in L of S1 intersection S2, that is L of S1 linear span of S1 intersection L linear span of S2 is a subset of L linear span of S1 intersection S2. From this and this, I can conclude linear span of S1 intersection linear span of S2 is equal to linear span of S1 intersection S2. Hence the proof. Next property, S is a subspace if and only if linear span is equal to the set itself. First, let S be a subspace. We know that linear span is the smallest subspace containing the set S. So S is a subset of L of S. This is from the theorem on linear span. Next, if summation alpha I Bi belongs to the linear combination S, then Bi belongs to the set S and alpha I belongs to the field. As S is a subspace, alpha I Bi belongs to set linear, that is from the scalar multiplication property of a vector space. Okay, as S is a subspace, as S itself is a vector space, so alpha I Bi belongs to S. Then its vector summation alpha I Bi also belongs to S. Therefore, taking any element, I am getting the element in the set S. Take any element in the linear span, I am getting that element in the S. So linear span is a subset of S. From this and this condition, I will get the equality, that is linear span is equal to the space subspace S. Conversely, linear span is equal to the linear span of S is equal to the set S. As linear span is a subspace and it is equal to S, so S is subspace. So if S is a subspace, linear span of S is equal to S, and if linear span of S is equal to S, then S is a subspace. Next, fifth property. Linear span of S is equal to linear span of S. Since linear span of S is the smallest subspace of V containing Ls, this is from the theorem on linear span. So, but L of S is a subspace. So, linear span of S is equal to S. That is this from the previous property. If S is a subspace, linear span of S is equal to S. So here linear span is subspace. So L of Ls is equal to S. L of S. Next is example on linear span. First example, so that the tuple 2 minus 5 3 is the linear span of these three vectors. That is 1 minus 3 2, then second vector 2 4 minus 1, and third vector 1 5 minus 7. Let A, B, C be any three scalars such that 2 minus 5 3 vector 2 minus 5 3 is a linear combination of A with the first vector 1 minus 3 2, it with B, and second vector 2 4 minus 1 plus C with third vector 1 5 minus 7. After calculation, you can find out the equation. This A plus 2B plus C equal to 2 minus 3A plus 4B minus 5C equal to 5, 2A minus B minus 7C equal to 3. Here you should apply the scalar multiplication. Multiply A with this element, and A with this element. Likewise, you should find out the value for the second two terms. Then add this pairwise, then equate left hand side and right hand side. You will get this equation. Here the right hand side is non-zero. So this system of equation are non-homogeneous linear equation. Next, solve this system of equation by using the method of non-homogeneous equation. So write it in matrix form. Here coefficient matrix A is obtained from the coefficient of ABC in the three equation. In the first equation it is 1, coefficient of A is 1, so it is 1. Coefficient of B is 2, it is 2. Coefficient of C is 1, so it is 1. In the second equation, coefficient of A is minus 3. Replace it by minus 3. And in second equation, coefficient of B is minus 4, is plus 4, not minus 4. So it is 4. Coefficient of C is minus 5. So replace it by minus 5. And coefficient of A in the third equation is 2. Coefficient of B is minus 1. Coefficient of C is minus 7. Then B, here B is the column matrix obtained by taking the right hand side of this equation, that is 2 5 3. So here, look here, if in the initial stage if you done the mistake, then this mistake will be propagated up to the end. In that case, you will never get more than 2 marks, even if this question asks for 5 marks. So you should be very careful while writing this equation. So as you know how to solve the linear equation, I am not correcting this one. So you should replace this 3 by minus 3 and proceed as it is. You will get the solution. Here, this answer is not correct. You should correct it by your own and submit your answer by next Thursday. So here, next, we define the argumented matrix. I am giving you the method. No, I'm not giving you the calculation, as you have already know how to find out plus and minus. So next, define argumented matrix A and B, which is the combination of the matrix A and B. Next step, my argumented matrix is defined. So I'm going to find out the rank of this matrix by echelon form. What is echelon form? In echelon form, make this element 1. First, check out whether this first element is non-zero or not. If it is 0 element, then check out where I will get the non-zero element. You should use row transformation to find this, to get a non-zero element here. After getting this non-zero, you will make this element unity in order to reduce the calculation. After making this element unity, with the help of this element, make all the remaining elements of this column 0. Below 1, make all the elements 0 with the help of proper row transformation. As here it is, I have done a mistake. I have write 3 instead of -3. You should correct it and write here -3. To make -3 0, you have to multiply this equation by 3 and edit with this equation. So use proper transformation. Then here again, to make this 0, multiply this row by 2, then subtract it from this, you will get this 0 and this 0. In echelon form, we use only row transformation. We never use column transformation. We use column transformation only to make this element 1 or non-zero. So these are my transformation, as I have done the mistake while writing the coefficient matrix. So this calculation are incorrect. So you should correct it and perform the calculation. In case of any complications, any doubt, we will discuss the same in our college. So here I am getting this one. This one final argumented matrix is this one. This is the rank of the argumented matrix is 3. Here rank of the coefficient matrix is 3. Your final answer is same, although this element is I have done mistake. Here rank will be 3. Rank of argumented matrix is 3, which is the rank of the coefficient matrix. Therefore, the system of equation is consistent. So, as rank of argumented matrix is equal to rank of coefficient matrix, hence 2 minus 5, 3 is the span of the given 3 vectors. Next question. If in V equal to R for R, if we consider the set as to be the collection of two elements 2, 0, 0, 1 and minus 1, 0, 1, 0, find the linear span of S. We consider any element A, B, C, D in the linear span of S. That is linear span of S, linear span of these two vectors. Then A, B, C, D will be equal to linear combination of these two elements. Alpha 2, 0, 0, 1 plus beta minus 1, 0, 1, 0. Alpha beta belongs to R. In next step, by using multiplications of the n tuple and then addition, pairwise addition of the tuple, I am getting ABCD equal to 2 alpha minus beta 0 then beta alpha. That is, take any element in linear span, it will be the structure of that element is this. So linear span will contain only this element. So here linear span is consists of 2 alpha minus beta 0 beta alpha. Alpha beta belongs to R. These are your question for practice. Next is sum of two subspaces. Let the W1 and W2 be two subspaces of a vector space V over the field F. Then the sum of W1 and W2 is given by W1 plus W2 is equal to U plus P, collection of all elements of the form U plus P, where U belongs to W1 and P belongs to W2. Next is theorem on subspace of two vector space. Let W1 and W2 be two subspace of a vector space over the field F. Then their sum W1 plus W2 is a subspace over the vector space V F, and it is the smallest subspace containing W1 union W2. Now come to proof. We consider two elements x equal to x1 plus x2, y equal to y1 plus y2 belongs to w1 plus w2. That means x1 y1 belongs to w1, x2 y2 belongs to w2. If alpha beta are any two scalars, then alpha x plus beta y is equal to alpha. Put the value of x, it will be x1 plus x2 plus beta, put the value of y, that is y1 plus y2. Then use the property of scalar multiplication. I will get alpha x1 plus alpha x2 beta y1 plus beta y2 in the right hand side, and left hand side remain as it is. Then in the right hand side, I will do the arrangement. I am writing alpha x1 with beta y1. Then in the second term, I am writing alpha x2 with the b plus beta y2. Since alpha beta belongs to F and x1 y1 belongs to w1, so alpha x1 plus beta y1 belongs to w1, as w1 is a subspace. So and alpha beta are scalars, so alpha x1 plus beta y1 belongs to w1. This is from the property of subspace. A non-empty subset w of a vector space V is a subspace if x comma y belongs to w, alpha beta belongs to alpha beta comma beta belongs to field, then alpha x plus beta y belongs to w. Using this property, I am getting alpha x1 plus beta y1 belongs to w, and similarly you can conclude alpha x2 plus beta y2 belongs to w2. So I have already explained these two concepts. Therefore, alpha x plus beta y belongs to w1 plus w2. Hence, w1 plus w2 is a subspace of P. Next, if u belongs to w1, then I can write u equal to u plus 0 belongs to u already belongs to w1, 0, as w2 is a subspace, 0 belongs to w2. That means u can be written in this form, and that can be belongs to w1 plus w2. Therefore, take any element here. You can take any element in w1. I can write in the form that element belongs to w1 plus w2. That means w1 is a subset of w1 plus w2. Similarly, I can show that w2 is subset of w1 plus w2. Take any element v in w2, then v can be written as v plus 0, that belongs to w1 plus w2. So w1 w2 w1 comma w2 is a subset of w1 plus w2. That means w1 union w2 is a subset of w1 plus w2. Okay, this is the condition. w1 union w2 is a subset of w1 plus w2. What we are going to prove that w1 plus w2 is the smallest subspace containing w1 union w2. For that, we will consider any subspace containing this. That subspace will contain w1 plus w2. Then our proof is done. For that, we consider S to be any subspace of P such that S contain W1 union W2. Okay. Next we consider any element U plus P belongs to W1 plus W2. Then U belongs to W1, P belongs to W1. So that U comma B belongs to W1 union W2, and W1 W2 is subset of S. S is a subspace. So using the if S is a subspace, then using property of subspace, the subspace is closed under vector addition. U plus V belongs to S. That means this W1 plus W2 is a subset of S. Given any subspace of vector space V over the field F, if it contains W1 union W2, then it must contain W1 plus W2. That is, W1 plus W2 is the smallest subspace of P containing W1 union W2. Hence the theorem. Next is definition of linearly dependent set and linearly independent set. A set of vectors P1, P2 up to Vn of vector space V is said to be linearly dependent. In short, we said LD if there exist scalars alpha 1, alpha 2 up to alpha n, not all these alphas are 0, such that alpha 1 V1 plus alpha 2 V2 plus alpha n Vn is 0. That is, their linear combination is 0. Next is linearly independent set. A set of vector v1, v2, v3, vn of a vector space V is said to be linearly independent if there exists scalar alpha 1, alpha 2, alpha n such that their linear combination is 0. Then all these scalars are 0. Then we said that set of vector v1, v2 up to vn are linearly independent. An infinite set S is linearly independent if you take every finite subset of that infinite set, take any finite subset. If that finite subset is linearly independent, then we say that the infinite set is linearly independent. Next is theorem on linearly independent and linearly dependent set. Two vectors v1 and v2 of vector space Vf are said to be linearly dependent if and only if one is scalar multiple of other. First, we are going to consider v1 and v2 are two linearly dependent vectors. Then there exists, by definition of linearly dependent, there exists scalar alpha 1 and alpha 2, not both 0, such that their linear combination is 0. Next, as not all alpha i's are 0, we consider alpha 1 is not equal to 0, as alpha 1 are field element, so inverse exists. Whenever alpha 1 is not 0, alpha 1 inverse exists. Multiplying this equation by alpha inverse, so I am getting this one. Here it is unity. Alpha 1 inverse into alpha 1 is unity. Here this is 0 by the properties of vector space. So v1 plus this term is equal to 0, which can be written as v1 is equal to minus of this term. From this I can conclude that v1 is a scalar multiple of v2. Conversely, v1 is a scalar multiple of v2. Say v1 is equal to alpha v2, alpha belongs to the field. Then I can write v1 plus minus alpha v2 is equal to 0. This is from the properties of vector space, that is I am writing minus alpha b2 in both sides. In next step, using properties of vector space, I can write alpha b2 minus alpha b2, again property of vector space. I am getting this one equal to 0. So finally I will get this equation, that is b1 plus minus alpha b2 is equal to 0 with at least one coefficient, that is 1 of b1 non-zero. b1 and b2 are linearly dependent. Hence the proof. Next, every finite superset of a linearly dependent set is linearly dependent. Let S be a linearly dependent subset of a vector space V and A be the superset of S. We consider S consists of element B1, B2, B1, B2 up to Bn, and A consists of element B1, B2 up to Bn. In addition with that, it will contain U1, U2, Un. Since S is linearly dependent, so there exists scalar, not all 0, alpha 1, alpha 2, dot dot dot, alpha n, such that linear combination of this scalar with this set is equal to 0. That is alpha 1 b1, alpha 2 b2 plus dot dot dot, alpha n bn is 0. I am adding this portion, that is 0 u1 plus 0 u2 up to 0 un. That will not change this equation. Okay, so this is the linear combination of the element of A. Here not all alpha I are 0. This implies A is linearly dependent. Next, if B1, B2 up to Bn are linearly independent, then none of the vector can be 0. Suppose Bk, where k lies between 1 and n, is 0. Suppose one of these vector is 0. Here we have to prove that none of this vector is 0. This set is linearly independent. To prove this, I have considered that suppose any one of them is 0. For instance, that will be Pk. Here k lies between any one of 1 to n. Okay. Then I can write this vector in this form: 0 into v1, 0 plus 0 v2 plus dot 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 0 vk minus 1 plus 1 bk, as bk is 0. This will not affect the equation, this equation. Then write the remaining vector with 0 coefficient. Then with at least one coefficient, non-zero coefficient, 1 of bk, this set of vectors will be linearly dependent, which contradict the fact that these vectors are linearly independent. Hence, none of these vectors are 0. As this problem, I am getting non-zero coefficient of a vector, as we have considered that one of the vector is 0, which is a contradiction. Therefore, none of the vector b1, b2 up to bn are 0. Next theorem, a subset of linearly independent set is linearly independent. Let S be a linearly independent subset of a vector space V and K is subset of S. Suppose K is not linearly independent, K is linearly dependent. Then S being the superset of K, S must be linearly dependent, which contradict the fact that S is linearly independent. Okay, therefore we have K must be linearly independent, and subset of linearly independent set is linearly independent. Next theorem, if b1, b2 up to bn are non-zero vectors, then either they are linearly independent or there exists k lies between 2 and n, such that Vk is the linear combination of its preceding factors. If the set of vectors b1, b2 up to bn are linearly independent, then we have nothing to prove. But if they are linearly dependent, then we have to show that this is a linear combination of preceding factors. So suppose the given vector are linearly dependent, then there exists a scalar alpha 1, alpha 2 up to alpha n, not all 0, such that their linear combination is 0. That is alpha 1 b1 plus alpha 2 b2 plus dot 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 plus alpha n bn is equal to 0. As this is linearly dependent, suppose there exists some alpha k that is not equal to 0. This k must be the least alpha k that is not equal to 0. Sorry, that is the big alpha k at most take the value of m. It does not exceed m. Okay. All other greater suffix will be equal to 0. Suppose alpha k not equal to 0 and all other suffix from alpha k plus 1 to alpha n is 0. That is, at the most, k may be equal to n. Okay? There, alpha k is the biggest suffix that not equal to 0. All other alpha k greater than all other suffix greater than alpha k must be equal to 0. And what is the maximum value of that k? Maximum value of that k is n. Okay? That is written. At the most, k may be equal to n. Next, we claim that k must be greater than equal to 2 because if k is less than 2, then alpha 1 b1 equal to 0. Since b1 is not equal to 0, we get alpha 1 is 0. b1 is not equal to 0. b1 are non-zero vector here given. Since b1 is not equal to 0, by using the properties of vector space, alpha 1 is equal to 0. This is not possible as here we have considered alpha k is the up to alpha k our no suffix will be equal to 0. So this is not possible. So we are getting a contradiction here. Therefore our alpha k is not equal to 0. Implies as alpha k is a field element, alpha k inverse exists. Thus k must greater than equal to 2 implies such that this happens from this condition alpha 1 b1 plus alpha 2 b2 plus dot 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 alpha n bn is equal to 0. From this equation I can write this equation. That means here above this equation, above this all the portion is 0. Then I have bk this is this one. So from this equation I will get in between alpha k bk plus alpha k plus 1 bk plus dot 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 alpha n bn equal to 0. All the bigger suffix alpha k plus 1 are 0. So it will goes up to alpha k bk. Then bring all this term alpha 1 b1 up to alpha k minus 1 b k minus 1 to right hand side. Then pre-multiply by alpha k inverse, I will get this equation. Okay, I will get this equation. Again, after calculation, I will get bk equal to this. This shows that bk is a linear combination of its preceding factor, hence the theorem. Next, given any set b1, b2, dot 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 bn of vectors, if bk is the linear combination of its preceding factor, then the set is linearly dependent. Suppose bk, k lies between 2 and n. I have explained why it is greater than equal to 2 in theorem number 5 of today's presentation is suppose bk is a linear combination of its preceding factor b1 b2 dot bk minus 1, then there exists scalars alpha 1 alpha 2 dot alpha k minus 1 such that bk is equal to linear combinations of these vectors, that is alpha 1 b1 up to alpha k minus 1 bk minus 1. Then I can bring this alpha k to right hand side. This can be written in this form. Then I have add this portion 0 bk plus 1 up to 0 bn, which will not change, which will not create any change to this equation, with at least one non-zero coefficient, that is minus 1 of bk. It will be minus 1 of bk. The set of vector is linearly independent. If U is a linear combination of vectors b1, b2 up to bn, then the set of vector u, b1, b2 dot bn is linearly dependent. Since U is linear combination of b1, b2 dot bn, so we can write the U in this form: alpha 1 b1 plus dot up to alpha n bn, where alpha i's are scalars. Then I can bring U to right hand side. I can write this one. Here minus 1 is a non-zero coefficient, so this set of vector is linearly dependent as the theorem. Now come to theorem number 8. If S is b1 b2 dot bn is linearly independent and U does not belong to the linear span of this set S, then the set consisting of U and this set, this element is linearly independent. Let alpha 1 alpha 2 be a scalar such that alpha u plus alpha 1 b1 plus dot alpha 2 b2 plus dot alpha n bn is equal to 0. If alpha is not equal to 0, then alpha inverse exists. Alpha is a field element. So this equation can be written in this form. With the help of calculation, I can write this equation to this form. So U belongs to the linear span, as this is the field element. So alpha is a field element. Alpha field is closed under multiplication. So alpha inverse alpha 1 is again belongs to field, and minus of alpha inverse alpha 1 belongs to field. So this is a scalar. And likewise, these are scalars. That means U is in the U can be written as linear combinations of the element of field and this set of vector. So U belongs to the linear span of S, which is a contradiction. So alpha not equal to 0. Here you must consider one more scalar, that is alpha. Let alpha comma alpha 1 dot alpha n be scalars such that alpha u plus alpha 1 b1 plus dot plus alpha n bn is equal to 0. So when alpha is equal to 0, from this equation I can write alpha, this is not alpha 1, this is alpha is 0, then alpha 1 is 0, there will be one more scalar. From this, no, it is all right. From this equation, you should correct only this one, alpha u, then write as here, it is alpha is 0, alpha 1 is 0, alpha 2 is 0, dot alpha n is 0. Therefore, S is linearly, since S is linearly independent set. From where I get alpha 1 is 0, alpha 2 is 0, and alpha n is 0. This is from the definition of linearly independent set, as b1, b2, bn are vectors of linearly independent set. As S is linearly independent set, so this alpha 1, alpha 2, dot alpha n is 0. Thus the set S1 is also linearly independent. Next is an example of linearly independent and linearly dependent. If V3R, that is R3 over R, and S is the set of three elements 1, 0, 0, 0, 1, 0, 0, 0, 1 is linearly independent, then set S collect, which is the collection of these three elements, is linearly independent set. If alpha, beta, gamma are three scalars, such that alpha into 1 0 0 plus beta into 0 1 0 plus gamma 0 0 1 and is equal to 0 tuple. Then by using the properties of addition and multiplication of tuple, I am getting alpha beta gamma equal to 0 0 0. Therefore, as is linearly independent set, that is, linear combination of the scalar with this factor is 0. That implies scalars are 0. Therefore, the set S is linearly independent set. Next, in V3R, that is R3 over R, verify whether the set given by this element is linearly independent or dependent. First, you consider three scalars alpha, beta, gamma such that linear combinations of the scalar with the vectors of S is equal to 0. That is, alpha with the first vector add up with the beta with the second vector plus gamma add up with the third vector is 0. Then use the properties of scalar multiplications and additions of the tuple that will give this second step. Then add the element pairwise, then equate the right hand side and left hand side, you will get this one. Look here, it is in the right hand side the element are 0. This means these are system of homogeneous equation. So solve this equation by the method for solving system of homogeneous equation, that is find out the rank of the coefficient matrix. Find out the rank of coefficient matrix. So put this in, find out the determinant of the coefficient matrix, that is 1 2 minus 3, 1 2 minus 3, then 2 minus 4 2, 2 minus 4 2, then minus 1 6 minus 5, minus 1 6, this is minus 5 or 5, minus 5, minus 5, here it is minus 5, this is typo, here it is written as minus 5. You can check out, find out the determinant, it will be minus 5. So find out determinant, it will be 0. This is typo only, okay. Here I am writing correctly, so this is minus 5. So I have not done any mistake here like the previous case. Here determinant is 0, so rank will be less than 3. If rank is less than 3, then the given system of equation has infinite number of equation, infinite number of solution, and therefore given a non-zero solution, hence the given vectors are linearly dependent. Next is a question for practice. These are your question set for practice. You should solve it. With this, your first unit is completed. If you have any doubt, any question, you are unable to solve some question in the practice session, then we will discuss it in college. Okay. Now, discussion class will be next Thursday from 12 to 12:45. You should attend my classes. We will discuss it. With that, I would like to conclude. Thank you. Remaining will be in the next class.